2016 London lecture entitled Climate Change and Antarctica, the Great Ice Sheets in the Past, Present and Future. My name is Graham Goffey. I'm the Treasurer of the Geological Society, and it's my pleasure to introduce today's speaker, Dr. Bethan Davies of Royal Holloway, University of London. The dynamics of the three great Antarctic ice sheets of East Antarctica, West Antarctica and the Antarctic Peninsula affect us all. If all the land ice in Antarctica melted, the world's sea level would rise by 58 metres. This is therefore highly topical in the Society's 2016 Year of Water programme. The West Antarctic and Antarctic Peninsula ice sheets are currently undergoing rapid change due to changing ocean currents, wind patterns and air temperatures. Dynamic effects in these smaller two ice sheets may result in rapid sea level rise of up to 3.5 metres over the next few hundred years. Bethan Davies is a glacial geologist interested in the interaction between glaciers and climate. She specialises in ice sheet and glacier reconstruction in temperate and high latitudes, using a combination of field studies, chronostratigraphic methods, especially cosmogenic nuclide dating, remote sensing and numerical modelling to quantify ice sheet and ice shelf history. Bethan is particularly interested in glacial processes at the ice-bed interface and uses detailed sedimentological analyses and micromorphology to analyse processes of entrainment, deposition and deformation. She lectures in physical geography at Royal Holloway, University of London. Ladies and gentlemen, please welcome Dr. Bethan Davies.
Good evening, and thank you for coming. Can I check that you can hear me in the back? Thank you. So I'm going to be talking about some of my own research that I've been involved with for the last 6 or 7 years, working on a small island on the northern part of the Antarctic Peninsula called James Ross Island. And this is a big project, and I've got lots of collaborators from lots of different universities, and some of the key ones are in my picture here. And I'm going to talk about the Antarctic Peninsula ice sheet over the last glacial maximum, so the last 20,000 years. And then I'm going to talk about some of the work I've done looking at glaciers on the James Ross Island over the last Holocene period, over the last 10,000 years or so. And I'll talk throughout about how this relates to modern changes on the Antarctic Peninsula. The rationale for this work is that Antarctica is changing. We're seeing rapid changes in atmospheric and ocean temperatures, and also on the glaciers that surround the Antarctic Peninsula. Esperanza is a research base in the northernmost part of the Antarctic Peninsula, and it has a long record of temperatures. And the positive degree day sum is the total of degrees above zero in a day. So if the daily maximum temperature is 2 degrees, then the positive degree day sum would be 2 degrees. And over the last 60 years, the amount of positive degree days has increased dramatically. So the number of days with temperatures above zero has increased over the last 60 years. And as we see more temperatures on the Antarctic Peninsula reaching temperatures above zero, we also see an increase in snowmelt. So this is the James Ross Island ice core record over the last 1,000 years. And over the 20th century, the last 100 years, we've seen a big increase in snowmelt. So the amount of snow melting with this increase in temperature. We've also observed glaciers thinning across the Antarctic Peninsula. So glaciers are having less snowfall and are melting more in their upper parts. So they're thinning throughout the glacier. They're also shrinking. So we have, this is slightly older now. This is from 2005, and I think the proportion has increased now. But glaciers across the Antarctic Peninsula are receding, so they're getting smaller. And it's important because it is contributions from these glaciers from the Antarctic Peninsula that are going to be important for sea level rise over the next few decades, in the next few hundred years. Potential collapse of the West Antarctic ice sheet or ice melting in East Antarctica may provide far more volume of seawater contribution, but it is the smaller glaciers on the Antarctic Peninsula with a short response time and that are more sensitive to climate change that are going to contribute to sea level rise over the next 100 years. And some of the biggest contributors are from the Antarctic and the sub-Antarctic. So under RCP 4.5, which is with aggressive climate mitigation and CO2 falling after 2050, we might expect a total sea level contribution from glaciers of 155 millimetres. And under RCP 8.5, worldwide glaciers may contribute up to 216 millimetres to global sea level rise over the next 100 years. And I know, sadly, today I think I know which scenario is more likely. As temperatures are changing across the Antarctic continent, winds are also changing. So we're getting an increase in the speed and an intensification of the southern hemisphere westerlies that flow around the Antarctic continent. And this is resulting in hotspots of warming and cooling, with the Antarctic Peninsula warming particularly rapidly. These winds are also important because they are deflecting the Antarctic circumpolar current that flows around the Antarctic continent. And as the Antarctic circumpolar current is deflected, warm water from mid-depths is upwelling and penetrating more deeply under the continental shelf. So this circumpolar deep water is flowing down these troughs on the continental shelf that were excavated by ice streams during the last glacial maximum. And because they're relatively warm, they're melting the ice from below. So they're melting the floating parts of glaciers and the floating ice shelves. Ocean melt of glaciers is really important because it is the largest source of ice loss in Antarctica. So we lose more ice through basal melt than through any other process in Antarctica. And in fact, half the meltwater comes from just 10 small ice shelves on the Southeast Pacific, down through the Antarctic Peninsula and West Antarctica. So just these little ice shelves here. As more circumpolar deep water is melting these ice shelves from below, we're seeing a change in ice shelf thickness. So these ice shelves are thinning and melting more rapidly. When you have a thinner ice shelf combined with increased atmospheric air temperatures, you create a system that is prone to catastrophic collapse. So if you have a thin ice shelf and a particularly warm summer, then you may get surface meltwater ponding on the ice shelf surface. This surface meltwater percolates down through the snowpack and through the ice and initiates a process of hydrofracture, whereby your ice shelf can catastrophically collapse over the course of a few weeks, over the course of a single summer. And over the last 30 years, we've witnessed ice shelves catastrophically collapsing in sequence from north to south down the Antarctic Peninsula. The ones in the north, like Prince Gustav Ice Shelf, have collapsed in the past, but the collapse of the Larsen is, as far as we know, the first time that has collapsed during the last 10,000 years. So this is beyond the normal behaviour of these Antarctic systems. Ice shelves are really important because they hold back and buttress the glaciers that flow into them. So these ice shelves are supporting the glaciers on land. When you remove the ice shelf, you change the dynamic equilibrium of the glacier, and the glacier flows faster in response. And we see a thinning as the glacier flows faster than the snowfall can sustain it. And this contributes directly to sea level rise. So ice shelf collapse in the Antarctic Peninsula has resulted in glacier acceleration and glacier thinning from those former ice shelf tributary glaciers. And we're concerned about the glaciers such as Pine Island Glacier and Thwaites Glacier that are some of the largest ice streams in Antarctica, which are supported by ice shelves that are thinning and have grounding lines that are retreating. So we're seeing this dynamic and rapid change in Antarctica today. But we have questions like, how normal is this? And what are the thresholds that govern this kind of behaviour? Under what circumstances will various ice shelves collapse? So we need to understand the thresholds that initiate this nonlinear dynamic behaviour. We need to understand tipping points that cause a rapid recession. We want to look at past ice sheet response because that will be the best predictor of future ice sheet behaviour. We want to put current change into a longer-term context that goes beyond satellite observations to understand the longer-term past rates and magnitudes of change. And we want to understand more about the processes controlling the dynamic and nonlinear behaviour of these glaciers. So I've been working on this project for quite a few years now, attempting to reconstruct the glacial history of the northeast Antarctic Peninsula over centennial to millennial timescales. And this is a nice iceberg from the Antarctic Peninsula. It's got lots of nice debris on that's going to fall out and fall to the bottom of the sea for marine geologists to puzzle over in years to come. So here is James Ross Island. It's a small island at the northeast tip of the Antarctic Peninsula. Because it is in the precipitation shadow of the prevailing westerlies, we have a relatively arid climate with one of the largest ice-free areas in Antarctica. It's separated from the Antarctic Peninsula by the Prince Gustav Channel, which is a deep channel with evidence of ice streaming at its base. And it used to be connected by Prince Gustav Ice Shelf until it collapsed in 1995. The island and the mainland have quite different geologies, which is helpful. So Trinity Peninsula is mostly high-grade metamorphic rocks, granites and gneisses, whereas James Ross Island is fossiliferous Cretaceous sandstones, flagstones, mudstones, with cap rocks of neogene basalts. So any granites that we find on James Ross Island are non-local and must have come from Trinity Peninsula, from this northernmost part of the Antarctic Peninsula. So here is Ulu Peninsula. This is where we were camped by Monolith Lake, and you'll see shortly why we called it Monolith Lake. This is Davy's Dome, which was named after an explorer from 1900, and sadly not after me. But we do have a glacier named after one of my colleagues. So we were deployed by ship just here in Brandy Bay, and we had ATVs to roam all the way around this large peninsula. And we were camped there for about 7 weeks, being self-sufficient through that time. So I'm now going to talk about the last glacial maximum around 20,000 years ago on James Ross Island. This is an Adelie penguin. They're very friendly. They're quite curious. Because Antarctica is cold, the geomorphic evidence left behind by the ice sheet is more subtle than you would expect, or more subtle than you would find in Britain. So we don't get the vast thicknesses of glaciotectonic sequences that we'd find in Norfolk or the large moraines that we might find in Britain. Instead, we have a much more subtle land system. So, for example, we have a scatter of basalt cobbles and ventifacts just distributed by the ice over this orange bedrock, which is the kind of the Cretaceous sandstone. And we also find rare granite erratics. And again, these erratics must have come from Trinity Peninsula, as they are not found on James Ross Island. There's no geology for them to be derived from in James Ross Island. And you can see that it has this kind of desert varnish, which is a red patina formed due to the arid and windy conditions that are derived there. And they also tend to be sculpted a little bit by the wind. And we find them isolated erratics on the tops of the hills up to about 380 metres above sea level. So they're right on the highest it's not a very high hill, but on the highest hills on James Ross Island, as well as being isolated boulders just on the general surface. In other parts of James Ross Island, like in coals and passes, places where we might expect ice flow to perhaps be funneled, we actually found evidence of much more increased deposition. So, for example, we have a granite boulder here, and scattered around the granite boulder are up to 50% of the pebbles are granite erratics. And I can tell you that because I counted a lot of pebbles. So we know that we have enhanced deposition down here. So we have very many more granite erratics, whereas in other parts of James Ross Island we see just rare scattered erratics. And then in the coastal areas adjacent to Prince Gustav Channel, we see ridges, so positive relief features with lines of boulders on them with abundant numbers of granite erratics. And so we interpret them as moraines. And you can see the white granite boulders here being very in stark contrast to the locally derived Cretaceous sandstones and flagstones and mudstones. And you can see little cobbles and pebbles of granite being very common in this very localized area. And then we have these Neogene basalt cap rocks that form a kind of mesa, a flat-topped hill, and they are very active periglacial block fields. So we see a lot of clasts being recycled. These cobbles and boulders are often, vertical because they're being recycled. So you need to be very careful about any boulders sampled on these block fields. And we find very rare granite boulders here. So we also applied a technique called cosmogenic nuclide dating, which assumes that a boulder left on the surface will accumulate rare isotopes after being bombarded by cosmic rays. Antarctica is a good place to do this because there are no farmers to move boulders out of their fields. The farmers in Northumberland are most inconsiderate. So we take samples using a hammer and chisel. You have to be very strong. I recommend having a strong field assistant with you. And we take about a kilo of rock from each boulder and take it back for crushing and analysis in an AMS. And it ultimately gives us an estimate of the amount of time that that boulder has been exposed to cosmic radiation. So it gives us an exposure age. We put all this data together to create a LAN System Model. So this is a kind of model that takes into account the active processes today and the landscape forming processes today on James Ross Island. So we have these block fields on the mesas with large landslides around their edges, with rock glaciers, and with small cold-based glaciers and ice caps on them. So ice caps with very little geomorphic expression around their edge. They're just cold. They're not really moving. Very little in the way of moraines around their edge. And then we have glaciers coming down from these ice fields, and they often are associated with very large, prominent ice-cored moraines. We have active marine processes around the edge, which are redistributing the sediments, a paraglacial redistribution of the sediments. And these stars indicate granite boulders that have been deposited across the island, some of them all the way on tops of these mesas. Lots of pattern ground and evidence of periglacial action, and in cols and passes, increased deposition of granite. The results of the cosmogenic nuclide dating show that the samples that we took on the higher hills are coming back with ages of around 18,000 years. So last glacial maximum ages. Whereas boulders on the interior coming back with ages of around 6,000 years, and then boulders in this area to the bounding the Prince Gustav Channel that is associated with a very enhanced deposition of granite boulders, youngs from around 12,000 years to 7,000 years. So we have a system coming down here that's younging in this direction. We interpreted these ages to suggest that during the last glacial maximum, thick, cold ice that had little geomorphic impact other than to distribute granite erratics amongst James Ross Island, overwhelmed the island, flowed directly across Prince Gustav Channel and across to Seymour Island and other islands to the east of this area. This is Seymour Island here, where we also have granite boulders. We then argue that during deglaciation, the ice sheet thinned and became more topographically constrained, with ice streaming being initiated in Prince Gustav Channel. And it is this ice stream that is responsible for the erratic rich drift and lateral moraines bounding Prince Gustav Channel. So we have our moraine coming down here at 7,000 years. And then we have local ice on James Ross Island. It's been cut off from Trinity Peninsula ice because there's a corridor of fast-flowing ice in the way that the ice cannot cross. We can put this together with other evidence from the area. So we're very fortunate to have the locally derived James Ross Island ice core record, which has a 14,000-year record of air temperature. We also have several detailed sea level records from the near area. And what we can see is this is age, years before present, and this is sample elevation. Our highest samples are coming out around the last glacial maximum, 20,000 years. But then we have a period of rapid warming, a period of rapid sea level rise, and in that time we get the initiation of our ice stream occurring in the low elevation areas adjacent to Prince Gustav Channel. So ice streaming is starting to occur as it becomes much warmer and as sea levels start to rise. So it is during the deglaciation that the ice stream is being initiated. We can put this together. So this was a large meta-analysis of much data with many, many authors that we ran. And these are all marine sediment cores, and we took all the data that we could find from terrestrial and marine data. And we're able to put together a review of ice sheet extent across the Antarctic Peninsula at 5,000-year time slices. So we can see ice streaming, ice extent at the continental shelf edge at the last glacial maximum. It's on the mid-shelf by 15,000 years, and it's pretty similar to present by 5,000 years ago. And we can also see that during the last glacial maximum, the Antarctic Peninsula ice sheet was formed of many ice streams that aren't in existence today. And these ice streams were flowing out to the continental shelf, with Prince Gustav ice stream flowing out here through Prince Gustav Channel number 15. So from this work, we can argue that because this ice stream is occurring during deglaciation, it's contributing to ice sheet drawdown. It's exerting a strong control on the deglaciation of the Antarctic Peninsula ice sheet. We can see that we're having rapid changes in ice sheet reorganization during deglaciation, and that these changes are influencing both the rates of deglaciation and also meltwater discharge. Because we used a terrestrial data set to complement a data set that is largely derived from the marine geological record, this is one of the first robustly dated examples of ice stream initiation on the northern part of the Antarctic Peninsula. We're actually able to say when ice streams started to flow, because the marine geological record gives us a very good snapshot of the last glacial maximum and subsequent recession. But by looking at the terrestrial evidence, we can start to think about ice stream initiation and how when ice streams began to flow. So I now want to talk about the Holocene, the last 10,000 years. So we were camped by Monolith Lake, and I think you can see why it's called Monolith Lake. It's in the middle of a boulder train of hyaloclastite boulders, which extends from this glacier, I'm standing on the moraine of this glacier, all the way to Brandy Bay Moraine, which is adjacent to Brandy Bay. One of the things that interested me about Holocene glacier behaviour on the Antarctic Peninsula was the apparent dichotomy between glacier advance and Holocene ice shelf collapse. We have good evidence from marine sediment cores that Prince Gustav ice shelf collapsed between 2,000 and 5,000 years ago. It wasn't in existence. And we know from the marine sediment, from the James Ross Island ice core, that this was a period of warming, which makes sense. We know that ice shelves disintegrate when it's warm. And that period was slightly warmer than today, so we would expect the ice shelf to be absent. But radiocarbon ages on shells underneath Brandy Bay Moraine, taken from around here, suggest that this re-advance occurred after 5,000 years ago. So people argued that you had this re-advance around 5,000 years ago, simultaneous with ice shelf collapse. So they argued that to drive a glacier re-advance during a period of regional warming, you have to have increased precipitation. So it has snowed more, which has driven this very large re-advance. And I was interested because we have warm temperatures today, and we have increased precipitation, but glaciers today are shrinking. So I thought this would be an interesting hypothesis to test, that during the mid-Holocene, a warmer but wetter environment forced a re-advance of this large glacier. This is another shot of the Hyaloclastite boulder terrain, and it goes right out to Brandy Bay Moraine in here. This is very close to our campsite, which is just behind this boulder over here. So the aim of our research was to test this hypothesis that a warmer but wetter climate forced this re-advance. And I used a numerical model, a single flowline model with the width-dependent shape factor to test this hypothesis. And this is the cross-sectional view. So here we have our glacier, and this is the land in front of the glacier. And then you can see that Prince Gustav Channel is extremely deep. This bathymetry data comes from the British Antarctic Survey. It's extremely deep, and so any glacier is going to reach here and then just start carving into the water. It's not going to extend any further. It's going to be limited by water depth, unless it's a big ice stream. So it's a one-dimensional finite difference flowline model written by my colleague Nick Gollage in Python. It simulates ice thickness evolution over 100 meters. It has a positive degree day scheme. If you want to know more about the model, I suggest we talk about it over a glass of wine after this lecture. It calculates mass balance using a positive degree day scheme with seasonality. So we have mean annual air temperature varying throughout the year, and also precipitation varying throughout the year. It has a summer precipitation regime, so summer, when it's warm, we're having more precipitation. And these data, we're fortunate to have so much data for this glacier because it's a very well-instrumented glacier. So we can have a very accurate portrayal of the climate. The Czech Geological Survey, which is based just here, they have produced a beautiful digital elevation model. We have bathymetry data from the British Antarctic Survey. The Czech Geological Survey have also got us measurements of ice velocity, ice thickness data. They also have these automatic weather stations. So it is one of the most instrumented and well understood glaciers on the Antarctic Peninsula, which makes it absolutely ideal for numerical modelling. And here again, we have the ice surface here, and this is just the run out in front of it. The cross section of this line going out here. The model was dynamically calibrated with temperature and precipitation data from the James Ross Island ice core. We only have precipitation data from the last 160 years, so I have a 160-year dynamic calibration. And I'm glad to say that the glacier stabilizes in a position that closely matches current observations, both the geometry and velocity. And its rates of recession from 1970 to 2006 are within areas of observations. So the glacier is receding, and it's receding at the same rate as we have observations. So we can hopefully have a bit of confidence that this is a good representation of reality. I conducted a whole series of experiments to test the reaction and behavior of this glacier. So one of them is a response time experiment where I applied a 500-year steady spin-up, and then I applied a step change of temperature and investigated how long it took the glacier to achieve equilibrium again. So you can see that as I make it warmer, the glacier very quickly achieves its equilibrium. So it recedes very quickly and then stays stable at that temperature. Whereas as I make it cooler, as the glacier starts to carve into the bay, my response time gets longer and longer. But the e-folding time, which is the time it takes the glacier to achieve around 2/3 of its response is between 100 and 400 years, depending on the magnitude of forcing applied. So it's a very responsive glacier that responds very quickly to climate change. I then ran a whole series of sensitivity experiments, and these are some of the more interesting results. So on the y-axis, we have glacier volume, and then we have temperature, precipitation. The degree day factors for snow and ice are how easy the glacier's snow and ice is to melt, so how much snow and ice melts per degree of warming. And the deformation factor is how easy the ice is to deform. And you can see that for most of these factors, we see very little change. Whereas for temperature, a small change in temperature forces a very large volume response. So as I get warmer, the glacier very quickly becomes smaller, whereas as I make it cooler, the glacier very quickly becomes very, very large. Whereas a plus and minus 20% change in precipitation forces only a very small change in glacier volume. This is glacier velocity, and again, you can see that for most of these factors, we have a relatively small response of the glacier to changes in precipitation and degree day factors. But we have a large change in velocity forced by mean annual air temperature. When it gets warmer, when the mean annual air temperature is around -5, the glacier accelerates because it becomes warm-based and it's sliding at its base, so it flows faster. But also, when we make it colder, the glacier also accelerates because it has increased gravitational driving stress, there's thicker ice, more ice, and so it flows more quickly. So this is just showing the same data. This is the temperature. So here we have blue is colder, and red is warmer. So as I make it colder, this is 2 degrees colder than today, the glacier is stabilizing at that break and slope, carving into that deep water. If I make it 2 degrees warmer than today, the glacier is just sort of hanging on in there, a little glacierette just about surviving. With a plus or minus 20% change in mean annual precipitation, we see only a change in glacier length of around 1 kilometre. So the glacier is not very sensitive to precipitation. It's much more sensitive to temperature. I wanted to investigate the relationships between temperature and precipitation a little bit more, so I ran many hundreds of experiments with each change in precipitation against each change in temperature. And so we have temperature on the y-axis and precipitation on the x-axis. And that black dot is the glacier's climatic input today. And the colour is glacier length. So you can see that as we make it colder and warmer, we have a big change in glacier length. But if I make it colder but wetter, I see only a relatively small increase in glacier length. This is the same data shown in a slightly different way. And what you can see is that the range of glacier lengths achieved when you have a colder temperature is much higher than the range of glacier lengths achieved at a warmer temperature. What's happening is the glacier is becoming more sensitive to precipitation as it gets colder. When we warm by a degree, we are losing a lot of the precipitation to rain. So when we're having more precipitation, it's simply being lost to the system. The snow is falling as rain and is therefore not contributing to the mass balance of the glacier. Whereas if we feed the glacier with lots of precipitation when it's cold, the glacier says thank you very much and gets much bigger. If we starve the glacier, it still grows because it melts less, but it grows. There's a bigger range of glacier volumes and lengths achieved. Climate models are forecasting an increase in precipitation with increasing air temperatures on the Antarctic Peninsula. But they're suggesting that the increase in precipitation will occur in the summer. So I was interested in how the seasonality of precipitation would affect the glacier. So here we have the temperature, so cold in the summer. Our summer is their winter. And around about now, we're just about here now, towards the end of the year, the warmer parts of the year. So this is the precipitation. The flat line is if precipitation is distributed throughout the year. And I changed the amplitude of precipitation seasonality from 1 through to 200%. So with a 200% amplitude, it's no precipitation at all at the minimum. And all the precipitation occurs in the summer. So I did that for both summer and winter. And what we're finding is that as I make the precipitation occur more in the summer, the glacier volume becomes less. Because as more snow falls in summer, more of that snow is falling as rain and is therefore being lost to the system. Whereas if I make the snow all fall in the winter, I still have quite a lot of glacial melt, so I have only a small increase in glacier volume. I thought, well, that's interesting. I'll run that with temperature as well. So I again ran a few hundred experiments. And this is with summer precipitation seasonality. This is the amplitude from 0 to 200%. And again, you can see that as I have a colder air temperature, we get a broader range of glacier volumes for a given precipitation seasonality. So again, the glacier is becoming more sensitive to precipitation seasonality as we get colder, and is less sensitive to precipitation seasonality as we get warmer. So the glacier is not helped by more snow falling in summer if we have any degree of warming, because so much of it is lost as rain. So I then used, once I'd got a good understanding of the glacier's systematic behaviour, I ran a series of transient simulations using the ice core temperature record from the James Ross Island ice core. I only have temperature data for the last 160 years, so I ran the model a number of times under different, with precipitation at different dependencies on temperature. So the James Ross Island ice core suggests that there is no precipitation dependence on temperature, but other people have suggested it might be anywhere between 5 and 50%. So I ran the model with a constant precipitation, which is this brown line coming up to here. I also ran the model with a 5% precipitation forcing, a 7.3% is a fairly common value used, 15%, 20%, and in desperation, 100% precipitation forcing. So 100% precipitation forcing, if it gets 1 degree warmer, there is 0 precipitation. And if it gets 1 degree colder, there is 100% precipitation. So I am really pushing this far beyond the bounds of plausibility in an attempt to force a re-advance around 5,000 years ago. But what you see is that during the early Holocene warming, we have a recession. We have a small recession during the mid-Holocene warming, and a very large, rapid re-advance in the last 1,000 years, when we have a period of cooling. As I change the amount of precipitation, so as I progressively starve the glacier in cool periods and feed the glacier in warm periods, I just see a dampened response. But I don't see really any change. So the glacier is still only getting large and only reaching that big moraine we found in the last 1,000 years. So I've got a little movie to show you, which hopefully will appear magically. Okay, so on the bottom graph is temperature, and then we have our little glacier fluctuating backwards and forwards. As we get into the mid-Holocene warm period, it gets smaller, and then as we reach the cooling in the last 1,000 years, it races out to reach that big moraine right at the edge of the bay. So we'll watch that one more time. I think what you can see from this is that it's likely the glacier has had minima similar to present at previous intervals, but is only going to have reached its largest extent when the climate gets cooler. Which makes sense, because it suggests that the behaviour we see today with concurrent glacier recession and ice shelf collapse is what happened in the mid-Holocene. To complete the experiment, I also ran it forwards in time with global climate change simulations for different GCMs for the next 200 years. So here we have temperature, here we have precipitation, and there's quite a lot of variability between the models for precipitation. That's because the models handle sea surface temperatures and sea ice in different ways. But under all four scenarios, we see strong recession with perhaps almost complete disappearance of the glacier in the next 150 years or so. So we have a decreased glacier size under all scenarios, even when precipitation increases. What I think this research shows is that the large glacial re-advance recorded here, it's one of the few glacial re-advances that we have evidence for on the Antarctic Peninsula, occurred 300 years ago, with its peak around 300 years ago. And I think we see that a warmer but wetter mid-Holocene optimum would have increased melt and driven simultaneous glacier recession and ice shelf collapse. I think this is much more logical because ice shelf collapse is associated with strong surface melt. And it's very difficult to see why you would get a big glacier re-advance. And I think we can also see that glacier minima, similar to present, have occurred many times throughout the Holocene. And it's quite, because of the nature of glaciers to eradicate the evidence beneath them, this can be quite difficult to see from the geological record, but the modelling suggests that the minima we're seeing today are not necessarily unusual. We reject the hypothesis that the glacier advanced during the Holocene in response to increased precipitation, which means that it is unlikely that the precipitation forecast to increase on the Antarctic Peninsula in the next 200 years will offset the strong surface melt and surface lowering that we're observing on glaciers in the northern Antarctic Peninsula today. I think the glaciers here are glacier melt is strongly controlled by mean annual air temperature and positive degree day sum in the northern Antarctic Peninsula. And changes in precipitation seasonality may exacerbate glacier recession. So if we are seeing an increase in precipitation, if it's occurring in summer, it will likely fall as rain and therefore be lost to the system. The Antarctic Peninsula is sensitive to these changes in climate. And it is likely that the northern Antarctic Peninsula glaciers will make a significant contribution to sea level rise from glaciers over the next few decades. Okay, so I'm going to wrap up. My field assistant was a far better photographer than me. That's his photo. We can conclude that ice streams were dynamic during the last glacial maximum. They weren't static features that existed through the whole glacial cycle, which is sometimes the impression that we get. Instead, they were dynamic, switching on during deglaciation and perhaps contributing to the very rapid drawdown and rapid recession we see during the late glacial. And this contextualizes some of the ice stream change that we see today in West Antarctica. So perhaps the ice streams draining into the Ross Sea, which we see turning on and switching off and accelerating. This is perhaps a normal response that happens during a period of climate change. And it highlights the possibility for rapid ice stream drawdown in the next few centuries. I think it's highlighted the importance of terrestrial geology. A lot of the research around Antarctica is strongly focused on the marine geological record, but terrestrial geological data can provide an important data set that can provide new and different and original analyses. And the Antarctic Peninsula has fluctuated considerably at centennial to millennial timescales. It hasn't simply been a straightforward case of largest at the last glacial maximum and straightforward recession since then. There have been fluctuations in the extent of the ice sheet. I think, however, that any increases in precipitation with increased air temperatures in the northern Antarctic Peninsula, I think are unlikely that they will offset the strong surface melt that we are observing today. And it is likely, therefore, that ice shelves will continue to collapse, that glaciers will continue to melt, and that the Antarctic Peninsula will be a significant contributor to sea level rise from glaciers in the next few decades. Thank you very much, and I'd be glad to take any questions.
If we have questions, please just give us a moment to get a microphone to you before you ask your question.
Do you have a reassessment then of the volume or rate of sea level rise then, based on the research that you've done?
So my research was on just one glacier, and I think to get an estimate of the rate of sea level rise from the Antarctic Peninsula, you would need to do a more comprehensive assessment of all the glaciers on the Antarctic Peninsula. But that would necessarily involve a number of simplifications, which is why it's interesting to do these sort of more detailed, smaller studies that are much better constrained, that you have fewer variables to estimate. There has been some recent research that has estimated more precisely the volume of glaciers by having a better understanding of the bed topography. And I think there is work ongoing with increased computer power to improve our estimate of sea level rise. But this work doesn't give an estimate of the regional sea level contribution.
Can you get local production rates for the cosmogenic isotopes at this site, and what are the approximate age uncertainties?
So their age uncertainties are, I think, around, it's going to take me ages to do that. They're around 10%. And I don't think there is a local production rate for Antarctica. We're using production rates for South America. So I think there's just not enough ice-free area to get a really good production rate from this area. But yeah, South America is fairly close to the Antarctic Peninsula, so we'll use that one. We also calculated these ages with a number, the Lalstone scaling scheme and various other scaling schemes. So in the paper, there are different ages using different scaling schemes and different production rates for completeness.
What are you going to work on next, or what are you working on now?
So I'm currently working on glaciation in Patagonia because it's slightly easier to get to. And I'm hoping to go back to Antarctica one day. But you can just fly to Patagonia and hire a car, so that's quite handy. But I'm still interested in the Holocene because I think it gives us a lot of insight into the southern hemisphere westerlies, and changes in the latitude of these southern hemisphere westerlies is particularly interesting for a lot of people at the moment because that may drive glacier fluctuations. So that's currently what I'm working on.
There's a question here.
Are there any data types that you're missing or that you'd like to have that you think would benefit this?
Oh, yes.
Such as?
Well, better chronological control is always welcome. Antarctica is difficult because the lack of organic matter makes radiocarbon dating difficult. The lack of sand accumulating in places makes optically stimulating data difficult. So I think better chronological control would always be welcome. Sea surface temperatures were fairly difficult to constrain in the model because most of the buoys measuring sea surface temperatures are on the other side of the Antarctic Peninsula. So it would be useful to have a bit more. It's a bit difficult because there's so much sea ice on this side of the Antarctic Peninsula. It's a bit difficult to have long-term monitoring data sets, and ships find it really difficult to get in. They get stuck in ice and stuff. So what else would I like? More precipitation data. That was one of the limitations of the work, was that I had to do the precipitation forcing on temperature under different scenarios because I didn't have an accurate record of precipitation. But again, that's more difficult than temperature in an ice core.
After the glacier, well, after the volume of the glacier will fall in the future, will it reconstruct in the same way as it reconstructed before, or will it change because of the level of CO2 in the atmosphere or other stuff?
Okay, so it's a good question. So the question is, will the make sure I've understood this correctly, will the glacier, if the temperature's warm, will the glacier behave like I've modelled it?
No, it's when it falls, when the glacier starts to reconstruct again.
Or when it gets bigger again?
Yes.
In the future?
Yes.
So if the question is, will the glacier re-advance centuries from now, if temperatures cool? I would like to think that if temperatures start to fall again because we have fewer cars, burn less fossil fuels, maybe we will see a glacier re-advance. If temperatures, I think it's unlikely within our lifetimes or our children's lifetimes that temperatures will cool enough to get a big re-advance like we saw in the late Holocene, because that was maybe a degree or two cooler than today. But maybe a few millennia from now, maybe. Depends on the change in the Earth's orbit and how that relates to carbon dioxide emissions and various complicated things that are beyond the scope of this talk.
I was thinking about that conceptual graph you had of the circumpolar deep water coming up these big troughs. And if you think back to the past tens of millions of years, we must have had hundreds of glacial advances and retreats and then re-advances. Do they tend, this is kind of off topic again, but do they tend to go out through the same troughs repeatedly? And does that subsequently deepen the troughs in a way that makes them more vulnerable to this CDW incursion as you progress through time?
Yeah, that's exactly what happens. So what we see during each subsequent glacial maximum over the last couple of million years is that the glaciers are reaching the continental shelf and are likely to have a fairly similar configuration to what they did on the last glacial maximum. And we can tell that because we have trough mouth fans at the end of these bathymetric troughs. And these trough mouth fans show that the glaciers reached that glacial margin and produced a load of debris out that. So we get stacked debris flows, which we can core and get a multi-million year record of glaciology showing that these glaciers are reaching this trough mouth fan in each glaciation. And it definitely does result in very deep bathymetric troughs, which are exploited, if that's the right word, by the warm circumpolar deep water.
Well, if there's no further questions, we can adjourn to the lower library for a while, and I'm sure there'll be questions for both of them in the lower library. If you haven't seen the Society William Smith map, or one of its William Smith maps, it's normally covered up by curtains, but the curtains are drawn back at the bottom of the stairs, so feel free to grab a glass of wine and peruse the map. Thank you all for coming to the lecture, and I hope you'll join me in thanking Dr. Davis for a marvellous talk. Thank you very much.